Okay, in this video I'm going to talk through another example of a limiting reactant problem involving a Mica table. And notice I'm asking you to convert everything that's left to grams. So this is going to be another one of those kind of all-encompassing 15-minute problems that you're going to be working on. So please copy this down, pause the video, write this down, and give it a shot. Try to solve it, and when you're done, we'll move on together. So assuming that you unpause, and let's start. So the first thing we always do is write our balanced formula. So lead 2 nitrate is going to be PbNO3 It's going to react with sodium iodide, NaI. So this is going to be a double replacement reaction. And see, did I tell you it reacts? Normally I would just tell you it's going to happen so you don't have to check the solubility table. We'll assume that does. In fact, I can tell anything with nitrate is always aqueous. NaI definitely aqueous. So we'll check the products. Lead iodide is definitely going to be solid. So I'll tell you that it happens just so you can save some time. Anyway, my products. My lead is going to mix with my iodine. But I need to preserve the charge on that lead, so it's a +2 before, it has to remain a +2 after. So it's going to be PbI2, lead 2 iodide, plus sodium nitrate, NaNO3. Okay, we have to balance this out. So 2 nitrates, 2 nitrates, 2 sodiums, 2 sodiums, 2 iodines, 2 iodines, 1 lead, 1 lead. We're good. Mole ratio, 1, 2, 1, 2. Alright, now we're given grams of each of our products, or reactants, so let's write these down, convert them to moles. So I have 27 grams of lead 2 nitrate, PbNO3 and I have 82 grams of sodium iodide. Times 1 mole over times 1 mole over. Okay, lead 2 nitrate. Lead is 207.2 plus N is 14.007 plus 3 oxygens is 48. 269.207 grams. Gram cancels gram. We get 0.100 moles. Nice clean answer. PbNO3 2. Lead iodide, or sodium iodide, excuse me, 22.990 plus 126.905. 149.895 grams. Gram cancels gram. 82 over that gives me 0.547 moles iodide. Okay, so this is what I'm going to produce, and I could tell right off the bat, unless my ratio is like more than 5 to 1, this is definitely going to be my limiting factor, because I mean it's 0.100 versus 0.547, but we'll check. So 100 and 547, I'm going to go back and write these in. So those are the moles of my product, or reactants that I have. Alright, so even if you know what the limiting factor is going to be, limiting reactant, it's still worth just solving it out, because you're going to need that information afterwards anyway. So, for lead 2 iodide, if we use PbNO3 2, we're going to get, well, look for a mole ratio, 1 to 1. So it's going to be the same. Now if I set this up with an x, I would say 1 over 0.100 equals 1 over x, cross multiply, x equals 0.100. So that's moles of lead 2 iodide. If you're using NaI, see how much we get. So it's going to be 2 over 0.547 equals 1 over x. Cross multiply, it's going to be 0.547 equals 2x. So this divided by 2 is going to give us x. 0.547 over 2 equals 0.2735. I'm going to round that off to a 4. 0.274 moles. So I look for which one's larger. This is larger, therefore that's my excess reagent. This must be my limiting reagent. This must be my excess reagent. So I think that's the first question I asked for. What's the limiting? What's the excess? Done. Sodium iodide, excess reagent, lead to nitrate, limiting reagent. Next, complete a Mica table. So I'm going to rewrite my formula. 2 PB, no, not the 2. PB NO3 2 plus NaI yields PbI2 plus NaNO3 2. So Mica stands for mole ratio, initial, change, and after. Okay, so my mole ratio is just copying down these coefficients. And now I'm going to plug in what I know. So these are my initial masses of my reactants. I'm going to copy them over the table. 0.100 and 0.547. Okay. How much of these do I have initially? 0. They're my products. Okay. My limiting reactant is going to be completely depleted. We already said that my limiting reactant is PbNO3 which is this, so I'm going to say minus 0.100, giving me 0 moles left over. Now here is a hint we're going to look for. What are my mole ratios? So when you see 1-to-1 mole ratios, you can fill in these numbers pretty easily. In fact, we've already kind of done this before. So since I lose 0.100 here, mole ratio is 1-to-1, I'm going to gain 0.100 here. Okay? This one actually, I think the reason these numbers were chosen is because you can do this all pretty much in your head. Mole ratio, 1 to 2. So if I produce 0.100 moles here, how much am I going to get out? 0.200. Okay? Mole ratio. If I produce 0.200 here, I have a 2 mole ratio, 2 to 2 or 1 to 1. So this much out means the same amount in, 0.200. So that's being used up, producing those. Okay? That's filled out. Now we just do the math. So this is going to be 0.347, 0.100, 0.200. It's my Mica table. It's all in moles, so this tells us the moles of everything that gets produced. Final step, convert everything into grams. So, NaI. How much do I have left? 0.347 grams, moles of NaI. And what else did I have? 0.100 moles of PbI2. And what else did I have? 0.200 moles of NaNO3. Converting all these into grams. So I need grams on the top. Now I should have these saved somewhere. In terms of molar masses, lead to nitrate 269. Now that's the one that's completely depleted, I think. Yep, Sodium iodide, 149.895. 149.895 grams per mole. Mole cancels mole. Lead to iodide. So it's 207.2 plus iodine times 2, so that's 2 times 126.905. 461.01 grams per mole. NaNO3 is going to be 22.990 plus 14.007 plus O3, which is 48. 84.997 grams per mole. Mole cancels mole. Mole cancels mole. Alright, solve these. 0.200 times this gives me 16.99. I had 3 sig figs originally. 17.0 grams of NaNO3. Here, I'm just going to take 10% of this. Show me the decimal point. 46.1 grams of PbI2. Here, I gotta actually do this out. 0.347 times 149.895 equals 52.0 grams of NaI. We are done. This is everything.